Okay, so we're back again. So with the in that previous one, we have seen that this thing, this is for single coil. But if you have more number of coils, then the shape of the MMF wave, that is, it will be like this. And if you add more and more, ultimately this will be taking the shape of sinusoidal waveform, right? So this side is your distance, and this is your MMF. This is the magnetic axis, right? And this side shown that everyone plus plus plus, this is dot 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 dot, so you know this, right? So by adding more coils, the MMF wave distribution shown in figure 6 may be obtained. We see that the MMF wave form is progressing from a square wave towards a sine wave, right? As coils are added, if you add more coils, so it will be your step slowly and slowly, it will be like a sinusoidal waveform, right? Though through use of your fractional pitch windings, the space harmonics can be made small. Machine design aims at minimizing harmonics, and for most analysis of machine performance, it is reasonable to assume that each phase winding produces a sinusoidal distributed MMF wave, right? So the windings are then said to be sinusoidally distributed. So the harmonics may be considered as secondary from the viewpoint of machine performance. So in this course, we will not study that harmonics and other things, but in the beginning, something we have to discuss, right? In addition to causing rotor surface eddy current losses, harmonics contribute to armature leakage reactance also, right? So now next is the rotating magnetic field. So this is phase A, phase B, phase C is marked. This is your A, and this is your minus. This is your B, and this is your showing is minus, and this is your what you call C, and this is your C minus, right? That is one. I mean, I told you one thing, that when if you take that in one side, the current entering into the page, right? If it is a plus, then leaving the your page, then it will be minus. So that is your plus or dot, the way we represent, right? And this is that your rotating magnetic field. This is phase A. Only phase A is shown, and it is a sinusoidal. Similarly for phase B and phase C, and this is your from the center of this thing. This is phase A axis, right? This gamma is measured in this direction, right? So if you this is actually spatial MMF wave of phase A. This is figure 7, right? So let us now determine the net MMF wave due to the three phase windings in the stator. So figure 7 shows the MMF wave of phase A. Only phase A we are showing. Similarly, phase B and phase C, that 120 degree apart, that you know, right? So in this case, your what you call gamma represents the angle along the periphery of the stator with respect to the center of phase A. So this is our center of phase A, right? And this angle is measured from this direction, that is gamma, right, along the stator periphery. So in this case, your what you call the MMF wave due to the three phases may be distributed as follows. We can write MMF for phase A. We can write K into IA into cos gamma. So this gamma is measured from this from this position. So it will be K is some constant. So K into IA say cos gamma, right? Similarly, your for phase B, it will be your you know this from ABC sequence, though it will be KIB cos gamma minus 2 pi by 3. And MMFC will be KIC cos gamma plus 2 pi by 3, right? Now where IA, IB, IC are the instantaneous values of the phase current, right? And K is a constant. Now each winding produces a stationary MMF wave whose magnitude changes as the instantaneous value of the current through the winding changes, right? The three MMF, your waves due to the three phases are displaced 120 degree electrical degrees apart in space. That we know, because from three phase studies we have studied, so you know all this, right? So now with balanced phase current, suppose if we are in this course, we will only consider the balance thing, right? And time origin arbitrarily chosen as the instant when IA is maximum, we have, you can write IA is equal to Im cos omega st, IB is equal to Im cos omega st minus 2 pi by 3, and IC is equal to your Im cos omega st plus 2 pi by 3. Only thing is that this equation number, it will be equation 5, not 3, right? It will be equation 5, right? So let me clear it. So omega s, that you know, that is, it is 2 pi f, that is your angular frequency of stator currents in electrical radian per second, right. The total MMF due to the three phases is given by MMF total, that is MMF A plus MMF B plus MMF C. So all these things you substitute, right, because MMF, here it is, here it is k into Ia cos gamma, k Ib cos gamma minus 2 pi by 3, and k Ic cos gamma plus 2 pi by 3. Value of Ia, Ib, Ic you substitute here from this equation. You substitute here. This is actually equation 5, right. So therefore, if you do so, it will be like this. And if you simplify, this simplification you please do yourself, right. Otherwise, it will consume more time. So this simplification, this is actually equation 6, not 4, right. I have written, but it is actually, I have written here, this is equation 6, not 4. It is equation 6, right. So if you simplify, it will be 3 by 2 k Im cos gamma minus omega st, right. Therefore, this equation is the equation of a travelling wave, right, which you have studied in power system course, right. So this equation, now it is basically it's a travelling wave, right, equation of travelling wave, and at any instant in time the total MMF has a sinusoidal spatial distribution. So basically it is function of cosine, so basically nothing but a sinusoidal distribution, right. It has a constant amplitude, that is your 3 by 2 k Im, the constant amplitude, and a space phase angle omega st. So this is your omega st, and your omega s is equal to angular frequency, that is 2 pi f, angular frequency of stator currents in electrical radian per second, right. So now this, which is function, thus the entire MMF wave moves at the constant angular velocity of omega s, right, electrical radian per second, because it is 3 by 2 k Im, right, cosine of your gamma minus omega st, right. And for a machine with PF field poles, suppose you have PF number of field poles, the speed of the stator field, right, speed of the rotation of the stator field, we know omega Sm will be 2 pi f, your 2 by Pf omega s, that is mechanical radian per second. This you know also from your synchronous machine studies. Or you can write Ns is equal to 120 f by Pf, or you can write 60 omega Sm upon 2 pi. This is your revolution per minute. This is equation 5a, this is I have marked as equation 5b, right. So this is the same as the synchronous speed of the rotor given by equation 3, actually it should be equation 3, it will be equation 3, not 1, right. So it will be equation 3. So this is the same as the your what you call the synchronous speed of the rotor given by equation 3. Therefore, for balance operation, the MMF wave due to stator current is stationary with respect to the rotor, right, because both are moving in the same speed. Therefore, for the balance operation, the MMF wave due to stator current is stationary with respect to the rotor. So now if we make it the MMF field, and for MMF for field and MMF for stator, right, stator MMF and field MMF, if you plot, this is your what you call, this is your MMF for stator, and this is for MMF for field, right. This is omega r and this is omega s, and these are your what you call, these are cut, and if you make it this kind of view, right. So this is Sn, that is the pole, and this is your omega r, the rotor speed, say, and this one your what you call, this is your 0, pi, 2 pi, this side is electrical radian, this is rotor, and this is your stator, stator field, the stator MMF, and this is your field MMF, right. So in this case, what will happen, the stator and rotor MMF wave shape, right, the magnitude of the stator MMF wave and the its relative angular position with respect to the rotor MMF wave depend on the synchronous machine load, right. So this is actually from your, I believe you have studied from your machine study, the magnitude of the stator MMF wave and its relative angular position with respect to the rotor MMF wave depend on the synchronous machine load, that is the output, right. That means the electromagnetic torque on the rotor acts in a direction so as to bring the magnetic fields into alignment. So, if the rotor field leads the armature field, the torque acts in opposition to the rotation with the machine acting as a generator. That means, if the machine acts as a generator, the rotor field leads the armature field, right, and the torque acts in opposition to the rotation with the machine acting as a generator. So, I will put a small question to you. This is your rotor field and this is your stator, that is your and this is your stator field, stator MMF and rotor MMF, right. So, from this diagram, if you make this kind of diagram, is it a generating mode or it is in motoring mode, right? This is a simple question to you, and answer is lying here. So, you will, when you go through this video and you put this your answer in the forum, right. So, if the rotor field leads the armature field, the torque acts in opposition to the rotation with the machine acting as a generator, otherwise opposite will happen. Or if the rotor field lacks the your what you call armature field, the torque acts in a direction of rotation with the machine acting as a motor, right. But our objective here for this course, throughout this, it will be your only synchronous generator, right. So, in other words, for generator action, the rotor field leads the armature field by the forward torque of a prime mover. Prime mover means, for a thermal power plant, it is a turbine, right. Therefore, for generator action, the rotor field leads the armature field by the forward torque of a prime mover. This thing you should keep in your mind as a general knowledge, right. For motor action, the rotor field lags behind the armature field due to the retarding torque of shaft load, that is mechanical type, right. So, next is the direct and quadrature axis. Now, magnetic circuits and all rotor windings are symmetrical with respect to both polar axis and the interpolar axis. This already you have studied in your electrical machines. Therefore, for the purpose of identifying synchronous machine characteristics, two axes are defined as shown in figure 1. That is your page 16. When you will go through this, I am not going back, right. So, it is figure 1. Just already we have seen d axis, q axis. So, that was on page 16. Now, the direct axis centered magnetically in the center of the north pole. That you go to the diagram 1, there you will see that already we have discussed. And the quadrature axis, we have what to call 90 degree electrical degrees ahead of the d axis. This is our what to call, we have made this way, but for this, as per your this thing IEEE standard. So, with this, just hold on, we will go to the next one. The selection of the q axis as leading d axis, I told you that q axis leading d axis by 90 degree, right, is purely arbitrary. This convention is based on the IEEE standard definition, right. Next, that will come to that your mathematical description of a synchronous machine, right. So, in developing equations of a synchronous machine, the following assumptions will make. The first assumption is the stator winding are sinusoidally distributed along the air gap as far as the mutual effects with the rotor are your concerned, right. This is the first assumption. Now, second assumption is that stator your slots cause no appreciable variation of the rotor inductances with the rotor position. This is another assumption. Third assumption is magnetic hysteresis is negligible, right. And another assumption is there, that is your saturation, right. So, another assumption is the magnetic saturation effects are negligible, right. So, these four assumptions will make, and your just hold on, and that assumptions your A, B, and C, these three assumptions are reasonable, right. The principal justification comes from the comparison of calculated performance based on these assumptions and actual measured performance. That means, theoretical and the measured, both were compared by you are assuming all these things, and they are very close to each other. So, these assumptions are more or less valid, right. So, and the fourth assumption is made for convenience in analysis. With magnetic saturation neglected, we are required to deal with only linear coupled circuits. making superposition applicable. For research and other research purpose, you have to consider everything, all non-linearities, right? But here for the classroom studies, we will only consider your what you call that your linear coupled circuit analysis, that kind of thing. So now this is your stator and rotor circuit of a synchronous machine, and omega r rotor angular velocity. Now here that your this schematically it is made like this. So actually this is your what you call that your stator side, and this is your rotor side. So stator, you have a three phase, your phase A, phase B, phase C. This is my phase A, this is my phase B, this is my phase C, and this is current leaving this terminal. Later I have mentioned, but I am telling you that when current leaving this terminal, we will take it as a positive convention, right, for the stator. And this is voltage EA, nomenclature I will give later, right? EA, EB, this is my EA, this is my EB, and this is my EC, the voltage. And this is the flux linkages of this what you call of phase A, this is phase B, phase C, and all these things you have to consider the mutual coupling also, right? Without that we cannot move. So this side is the stator part, and this is the axis of phase A. Now this is your what you call, this is actually EFD, I have written in other way, right? Actually this is your field voltage, DC field voltage, this is actually EFD. So this is EFD, right? And this current is IFD entering into the your what you call that your field winding. So this convention will be positive convention, right? And now you have Emerson windings, right, both along the D axis, along the Q axis, and they are short circuited by itself, and it is just in rotor is mentioned that is IKD. This is actually IKD, I have written in just other way, right? And this is your IKQ, this is your IKQ. So this is D axis and this is Q axis, right? And these two are Emerson. K represents actually your 0, 1, 2, 3. If there is no Emerson winding, right, then that means K is 0. Otherwise 1, 2, 3 like this. But hardly you will find more 1 or 2 such your what you call this Emerson windings. One will be along the D axis, another maybe along the Q axis, right? But for generalization, we will use that K, that notation K we will use. So IKD and IKQ, and this is the field current here, it is IFD, right? This is your IFD, and this is the rotation of the your what you call the rotor, and this is omega r electrical radian per second, right? And this is the axis of phase A, this is the axis of phase A, this is the axis of phase A, and this is D axis, and D axis leading your axis of phase A by angle theta, right? And then that means the Q axis, right, leading this one will be 90 degree plus theta, because this is your 90 degree. So 90 degree plus theta, right? So this is your what you call that your schematic diagram of synchronous machine, right? But when we write your, and this is the flux linkage psi A, psi B, and psi C in this direction, and this is EA, EB, and EC, right? So this is your what you call that your schematic diagram, and from this only we will write the equations, but later all the flux linkage equation we write, and we have to consider that your mutual one, that means flux linkage with your in phase A, right? That means mutual also due to current IB and IC, or also due to the field current, also due to the Emerson winding current IKD, IQ, all mutual effects we have to consider for detailed analysis, right? So this is a schematic diagram. So now the nomenclature is now given, whatever I said, ABC stator phase winding. So this is my ABC, the stator phase winding. FD field winding, that is here we are making no suffix FD here, and here also it is field winding FD, right? And KD D axis Emerson circuit, this is your KD D axis, and KQ Q axis Emerson circuit, right? And K is equal to 1 to n is number of Emerson circuits. If there is in that case, if you put suppose K is equal to 0, there will be no Emerson circuit, then this should not be there and this should not be there, but which is not reality, 1 or 2 will be there, right? So your theta is equal to angle by which D axis leads the magnetic your magnetic axis of phase A winding electrical radius per second. This I have also told you, right? So this is the nomenclature. Now, So figure 9 shows the circuit involved in the analysis of a synchronous machine. So this is your figure 9, and this figure 9 is not at the bottom, I have marked it as the top. This is your what you call, just hold on. So this is your figure 9, this is actually figure 9, I marked it on top, right? And omega r, the rotor angular velocity. So therefore figure 9 shows the circuit involved in the analysis of a synchronous machine, and from this circuit only we will write all these equations. After that, slowly and slowly we will develop the block diagram representation. So the stator circuit consists of 3-phase armature windings carrying alternating current. So this is your the stator circuit, it is carrying alternating current IA, IB and IC in 3 different phases, right? The rotor circuits comprise field and armature winding. So this is our rotor circuit. It has a field as well as armature winding on D axis and Q axis, right? And for the field winding is connected to a source of direct current. I have told you earlier, the field is given as a your what you call the DC voltage, right? So for purpose of analysis, the currents in the armature, that is a solid rotor and or damper winding, may be assumed to flow in 2 sets of closed circuit, because the circuit is closed itself, right? One set whose flux is in the line that if the field along the D axis, that means here, this one, it will be along the D axis, right? And it will be along the Q axis, and your what you call, and the other set whose flux is at right angles to the field axis or along the Q axis, right? That means this one, either it is along the Q axis or it will be right angle to the D axis. So the armature circuit, as discussed previously, take different forms, and distinct electrically independent circuit may not exist, right? So in machine design analysis, a large number of circuits are used to represent armature effects, right? For system analysis, where the characteristic of the machine as seen from its stator and rotor terminals are of interest, a limited number of circuits may be used. The type of rotor construction and the frequency range over which the model should accurately represent the machine characteristics determine the number of rotor circuits. For system stability studies, it is seldom necessary to represent more than 2 or 3 rotor circuits in each axis, right? So in figure 9, that is the previous figure, right? For the sake of simplicity, only one armature circuit is assumed in each axis, and we will write the machine equation based on this assumption. Then what will happen? Our analysis will be slightly simpler, right? Otherwise things will unnecessarily become complicated. Because synchronous machine itself, later you will find that things are very complicated, particularly those equations and small perturbation equations, you will find things are very complicated. So because huge mathematical developments are there, right? So that's why we will make only one each, but in general we will try to represent, that is your IKD or IKQ. So however, we implicitly consider an arbitrary number of such circuits that subscript k is used to denote this, right? So this is actually subscript k we have used, that is IKD, IKQ, right? Now from figure 1, it will be actually it will be your figure 1, it will be page 16, right? Just you go to, I am not going back again, right? So your page 16, your figure 1 and figure 9, theta is, this we have seen, theta is defined as the angle by which the D axis leads the central line of phase A winding in the direction of rotation. That already your just minute, that already I have told you, right? Here, right? The D axis is leading this one, phase axis of phase A by theta, right? So therefore, since the rotor is rotating with respect to the stator, right, angle theta is continuously increasing and is related to the rotor angular velocity omega r, and time t as follows. We know theta is equal to omega r t. No equation number is given here. No equation number is given here, right? The electrical performance equation of a synchronous machine can be developed by writing equations of the coupled circuit identified in figure 9. So this figure, actually we have to apply the coupled circuit and concept, and we have to write down all the equations like psi A, psi B and psi C, all these equations, and also the voltage equation EA, EB, EC, right? So all these things in terms of psi A and stator windings also have resistances, that also you have to consider, you cannot neglect that, right? So all these things we have to write using that coupled concept of coupled circuit, which already you have studied in first year. So question is that your now before going to do that, right, so as we have to study coupled circuit, so we will just brush up our memories, right? So what we will do that we have to review the magnetic circuit equations in a brief, because already you have studied the magnetic your coupled magnetic circuit in your first year these things, or if you want to brush up your memories for this particular thing, that in fundamentals of electrical engineering, the first year course which I have recorded and is ongoing now, right, there you will see that magnetic circuits and coupled circuits are explained in detail, right? So same concept will be applied, that but your what you call, just to brush up our memories before writing those your what you call that your synchronous machine equation, we have to review our magnetic circuit equations, right, in a brief. So first is a single excited circuit, right? So in this case you consider this is a coil, right? It is a coil, its number of turns is n, flux linkage is psi, right, and it has a resistance, say it has resistance R, right, and this is the current I, and this is the voltage plus minus, it is given E1, single excited magnetic, or what you call single excited magnetic circuit. Here no coupled circuit, only a single excited circuit, right, and this is the flux linkage, and this is the number of turns n. So you consider first the elementary circuit of figure 10. So this is figure 10, right? So comprising a single exciting coil, this is your coil. The coil has n turns and a resistance R, and it is assumed to have a linear flux mmf relationship. We will assume the flux versus flux and mmf, it is a relationship is linear. So the coil has n turns, I told you, and a resistance R. It is assumed to have a linear flux mmf relationship. Now according to Faraday's law, the induced voltage EI is given as EI is equal to d psi by dt, because this voltage actually it is EI, right? This voltage is EI. So here it is EI, right? It is EI, and this is the number of turns n. So EI is equal to n d psi dt, right? So therefore it is EI is equal to d psi by dt. This is equation 6. This is equation 6, right? And the terminal voltage then U1 is given by U1 is equal to your EI plus RI, but EI is equal to d psi by dt. So E d psi by dt plus RI. Not going back to the figure, it is understandable. Therefore the flux linkage may be expressed in terms of the inductance cell of the circuit. So we can write psi is equal to Li. This also you know. This is equation 8, right? Therefore the inductance by definition is equal to the flux linkage per unit current, right? So therefore we know that n phi is equal to Li. This is also you know, right? Therefore L is equal to n phi upon I. Now numerator and denominator you multiply by n, so it will be n square upon n square into phi upon ni, right? But permeance P is equal to phi upon ni, right? Therefore L is equal to n square into P, that is n square into permeance. This is equation 9, where P is equal to permeance of magnetic path. Therefore, and flux phi is equal to, right, flux from this equation only, and then flux phi is equal to, this phi is equal to flux is equal to mmf into P, right? That is from this equation. This is your mmf, right? Therefore phi is equal to ni into your P, that is ni into P, that is mmf into P, right? So next your what you call, so this is for simple linear circuit, right? And next we will take your coupled circuit. First before taking synchronous machine, but we'll thank you very much. We'll be back again.